Good afternoon, everybody, or good morning, also wherever you are. It is a great pleasure for me to welcome Ron Folman today for our CQT Institute colloquium. Ron will speak on matter wave interferometry on the atom chip. But let me maybe please first introduce very briefly. So Ron did his PhD in 1998 at the Weizmann Institute and also at CERN. Then switched to the AMO field to work with Jörg Schmidtmeyer in Innsbruck. And I think then you also moved with Jörg Schmidtmeyer to Heidelberg. Is that correct?
Yes, yes.
Yeah,
actually,
yeah.
The person who invited me to come and do a postdoc in Innsbruck, Anton Zeilinger.
Yeah,
and then
I see.
Worked with him, and then I went with Jörg to Heidelberg. Yes.
Yeah. So since that initial postdoc time in Innsbruck and in Heidelberg, you are very well known for your contributions and for your innovative work in chip traps with cold atoms. Since 2003, you are at the Ben-Gurion University in Negev in Israel, pursuing these types of projects, and have also really enhanced your portfolio and increased your group very impressively. Today, it's about the chip traps and the atom interferometry. Well, if I may say, that is a mature field in some sense, which might sometimes be surprising in light of all the new formulations of how we, think about quantum technologies. But in spite of being a mature field, there are always kind of new conceptual developments that are emerging, and Ron will tell us really exciting news about these kind of developments today. And some time ago, when Bose-Einstein condensation was achieved, people were saying, it took about 70 years from the prediction by Bose and Einstein to the pure experimental realization in cold gases. So now with this Stern-Gerlach interferometer, it's approximately 100 years, if I understand that correctly. So maybe the field is not that mature, but certainly I'm very excited about your talk today. So thank you very much for accepting, and the floor is yours.
Thank you, Kai, for this kind introduction. So the title is Matter Wave Interferometry on the Atom Chip, and I will combine it with the 100-year anniversary to the Stern-Gerlach experiment, and talk quite a bit about Stern-Gerlach interferometry on the atom chip. So what you see here are different pictures. I will actually not go over them now, and I hope that by the end of the talk you will know what each one of these pictures represents. I will just tell you that what you see here, I hope you can see my pointer, is one of the first atom chips that we produced in the new fabrication facility that I built in Ben-Gurion University, dedicated to quantum optics on chips. And this is one of the first chips that we produced, and the experiment itself was done in Heidelberg. I sent the chip to Heidelberg because we still didn't have a BEC back then. And on this chip, we were able to see really nice things that have to do with electron transport. Maybe I'll say a few words about that, but generally this is how an atom chip looks like. And of course, in Singapore, you have a great group for atom chips, the group of Rainer Dumke. And actually, I'm happy to say that we have just received a joint grant together. And so we will be developing atom chips together. All right, so 100 years to the Stern-Gerlach experiment, and actually they went into their lab 102 years ago. So that was in 1919. And 2 years ago, there was a fest in Frankfurt in the original building that still stands. You can see here this building, which still stands, where the experiment was done. And it was a very nice fest in honor of this event. of them going into the lab in 1919, and it's becoming now a European Physical Society historic site. Here you see Stern and Gerlach. Between them, by the way, just an anecdote, is Lisa Meitner, who also worked in Berlin, in Germany. She worked in Berlin with Otto Hahn. Actually, the interesting thing about her is she got nominated for the Nobel 48 times. I think she holds the record, maybe, I'm not sure, but she never got the Nobel. Okay. You all know these pictures and the story about the cigar of Otto Stern. By the way, Otto Stern is buried in Berkeley. He had to escape from Germany because he was Jewish, and he went to the US. If you think the Stern-Gerlach experiment is simple experiment, well, people, quite smart people, are still writing papers about it. I would say that this experiment is still, the theory of it is quite complicated to understand. It's not as simple as the textbook for undergraduate studies make it to be. All right, so there's still people, a lot of people writing all kinds of effects about the Stern-Gerlach. I will not go into these papers, just to show you that people are still very much interested in this kind of experiments, the Stern-Gerlach experiments. So this is one paper. Here I found another paper from recent years. I will not go into these papers, just to show you that people are still very much interested in this effect, which is sometimes called a paradigm of quantum theory. So the outline of my talk is a quick reminder of what the atom chip is, Stern-Gerlach interferometry, which would be the main theme of the talk, then some applications of Stern-Gerlach interferometry. For example, we did clock interferometry, and another spin-off, which is geometrical phase, which we measured. And then maybe if time permits, I will even tell you about a harder Stern-Gerlach interferometer that we're now building, which has to do with quantum gravity. What you see around you are pictures from the desert. So we are only about an hour south of Tel Aviv, but we're in the middle of the Israeli desert. Israel is actually split. The north part is green and the south part is desert. And we're in the middle of the desert. So you see camels around the campus. Also all kinds of deer actually are flourishing in the desert because they have water holes from which they can drink. And I always like to take my students to all kinds of hikes in canyons because the water is really doing amazing fabrication. And I always say that the water is teaching me how to fabricate deep trenches in the chips. So these are my students. And if you want to finish a PhD with me, you have to also be able to do these hikes. Sometimes I take my students flying, as you see here, in all kinds of air motorbikes. This is called an ultralight. And I have 100% success in these statistics. They never ask for a second flight. I'm not sure why, but that's the statistics. Okay, so I will not talk today about quantum technology, but of course, like every other group that does quantum science, we also do quantum technology. Just to flash at you what we're doing, this is an example of a microwave atomic clock, a miniaturized, compact microwave atomic clock. What you see here is a small pyramid knot. Yeah, and you see the atoms here. This green dot is the atoms. This thing is very small. And you see here mu metal shielding. Everything here is vacuum. Also, you have to make sure this is a microwave cavity. You have to make sure that your microwave field is very homogeneous. And here you see real pictures of the atom. Only one cloud is real. The others are fake or reflections of this cloud here below this pyramid knot that you see here. And only one beam of light does everything, all the cooling. Here you see a more advanced clock. It's a ytterbium optical clock. We're part of a European consortium that is trying to move the standard of the second from microwave clocks, which is where it is now, to optical frequency clocks, strontium or ytterbium. And so we're part of this European consortium for optical frequency clocks. We're developing a ytterbium clock in our lab. Here you see, it's hard to see, but it's a cell of vapor atoms, fiber going in, fiber going out. This is an all optical magnetic sensor. This is the size of the palm of your hand. And so we're developing all these things, including acceleration sensors, rotation sensors. And here is a picture I love. What you see here is really a magnetic sensor that is built out of NV centers, nitrogen vacancy centers in diamond. So we put a thin layer of these NV centers in diamond above a IPCO superconductor. And these NV centers that are sensitive to magnetic field were able to image these vortices. What you see here are actually fluxes of magnetic field coming out of vortices. And we hope that with this new sensor, we would be able to help theoreticians that work on high TC superconductors. Okay, so of course, the atom chip has been around, like I said, for some 20 years. And this is actually an artist's view from a long time ago, a paper by Jakob Brakel. He was at the time in Garching together with Ted Hensch. They were one of the groups that initially started the business of atom chips. I was, as Kai said, with Jörg Schmidmeier, Anton Zeilinger, we were another group that started the business of atom chip. There were several groups that together worked on it. And here you see some wires, electrodes. I will say a little bit more about that. And here you see maybe a BC or a cloud of atoms, a few microns above the surface. By the way, this conveyor belt, what you see here is actually a conveyor belt that can move the 3D potential, 3D minimum from side to side. This is an invention of Ted Hensch. I always like to hear his story about it. He says that he first thought about it in a restaurant and made this drawing, first of all, on a napkin in a restaurant. So that was a really nice invention by Ted Hensch, who we all know and love. So in the lab, of course, you see these wires. You see one cloud is real, the other cloud is a reflection from the surface, and the distance between these clouds tell you how close you are to the surface. Although it's 20 years old, the atom chip is actually, the definition of the atom chip is expanding. People started 20 years ago with ground state atoms, but now people are using Rydberg atoms for quantum computation, cold molecules, even NV centers to get very accurate magnetic fields, cold ions, cold electrons. And now we even have a project for antimatter to trap antihydrogen very close to a regular matter surface on the atom chip. This is a project with CERN. And so the atom chip definition is broadening all the time in terms of the particles that are being used. Our facility is servicing many labs around the world. For example, this is a chip we sent to Germany. You see here 2 ions trapped on it. This is a permanent magnet lattice that we sent to Amsterdam. You see here atoms trapped. This is fluorescence from atoms trapped in this magnetic lattice, permanent magnet lattice. Here is a permanent magnet loop that we sent to the UK for doing Sagnac interferometry. So we are sending to all kinds of labs advanced chips. This is the vision of the chip, of how the chip would look like in the future for quantum technology. So this is just 0.5 millimeter, 500 microns thick. It's a silicon wafer. I took this beautiful picture and this design from Southampton, from Tim and Matt. And the idea is that inside the silicon wafer, you would have the vacuum chamber, you would have your pump, you would have your particle source, and maybe a MEMS valve between the bad vacuum and the good vacuum, and some lasers for cooling, permanent magnets, current carrying wires, and then read out with some cavity QED and electronics and fibers going out. And this is not so far into the future. Several groups around the world are working on it. And this is one design. I was not long ago in Southampton and actually held it in my hand. So all this is very nice in terms of prospects for the future. And if you're really interested in the history, so a few years ago, we put this very detailed review, maybe 400 references, if I remember correctly, on the archive for you to see. 2 chips have already made it into space. One by the German Space Agency with groups like the group of Ernst Russell making a lot of the work. And here you have the atom chip right here with the 2D MOT feeding it. And they were able to do a BEC all the way through their space voyage. Very beautiful work. And now another atom chip made by Colt Quanta, the company founded by Dana Anderson, is now on the International Space Station. Already this system is working. We're also sending chips to the US Air Force. I cannot give you details about this chip, but it's really interesting to see how the whole business of the chips is moving forward. And here is already the chip for the anti-hydrogen that I told you about. This is now being tested in the lab of Ferdinand Schmidt-Kaller in Mainz. It's part of the GBAR CERN collaboration. And here you see this is where the anti-hydrogen at CERN is being manufactured. And for me, it's really nice if the chip will indeed be installed there. It's closing a circle because I started my career at CERN. It will be a nice closing of the circle. And of course, chips are now going into the whole business of atomtronics. And we would like, for this, the first circuit we would like to really realize is this Sagnac loop. It's a CW Sagnac loop where you have tunneling barriers. These straight lines are tunneling barriers. And you have here a MOT beam going through the first beam splitter, 50-50 beam splitter, into two directions, and then going in two directions into this loop through this very low tunneling probability coupling barrier. And then they do many hundreds of turns here. And then CW again, continuous wave going out. So you get a continuous signal coming out of this device. We're starting to fabricate these kind of things. This is actually a 4-layer fabrication. These chips are quite complicated. And it's very interesting. The theory for this, by the way, is already out there for some years in a paper that we put there 13 years ago, 14 years ago already, for the CW Sagnac configuration. What is very interesting about chips, people, when chips started 20 years ago, people thought that you cannot do a BEC close to the chip because of the heating. For example, black body radiation from the room temperature surface would hit the atoms, and people did not believe it. And then came the first BEC, I think it was Tübingen, that put the first BEC close to the chip, and people were actually very surprised that the heating rate was very low. But now the surprise is even larger. What we did here is we took a BEC and we put it in this grating potential, just like when you send light into a grating potential. And we did this grating potential by this snake-like wire, current-carrying wire. So we put the atoms very close to this, and these the electrons that are going like in a snake-like potential path are making this potential, and the BEC looks like that, like in a grating, and then you release it, and you see an interference pattern, and we can prove that even 5 microns from the chip, this is a room temperature surface with Johnson noise, black body noise, you still get very nice, very long coherence time, spatial coherence. I'm not talking about now spin coherence or internal level coherence, which is quite easy to get, but even spatial coherence, which is harder to get, you get it very nicely 5 microns from the surface. Okay, the properties we're going to use today for the Stern-Gerlach experiment, 2 very important properties. One is that you get very high gradients. And here I give you an example with just 2 amps and the atoms 10 microns from the wire, you get 40 kilograms per millimeter. And actually you could go even much higher. If you go to 10 to the 9 amp per centimeter square, and you go to 1 micron, you can go very high, up to 10 to the 6 Tesla per meter, which is many orders of magnitude, maybe 3-4 orders of magnitude higher than the best coils at CERN could get. So very high gradients coming from these wires. And another very good thing about them is because it's not a coil, low inductance allows you a very quick on-off cycle. Yeah. This is an example. The chip is here, and this is an example when all states, MF states or Siemens sublevels of an atom are filled in a BEC, you get all these, and you apply a current and a gradient, you get all these clouds coming from the different Siemens sublevels. Okay, so Stern-Gerlach splitting is well known. You know it from your textbooks, but there's a It's like a beam splitter, a regular light beam splitter with a twist. You have an entanglement between momentum and spin. That's the twist. And you can even do it with charged particles. We put this paper 2 years ago. We published this paper that you can even do it with charged particles, and we're thinking about doing it also with charged particles, but today I will only speak about neutral atoms. So even if you just do this entanglement, you can already play some really nice games. This is an idea that came to us from a theoretician, Juan Pablo Paz, and his group. And he says, even if you can just do a splitting, nothing more, no interferometry, just a splitting. This is an entangling operation between motion, that's the momentum, and the electronic state, that's the spin. And if you do this entangle operation, you can treat the position or the momentum after time of flight is position as an auxiliary qubit. And then you can actually do this entangling operation, then drive the system, do some work on the system, and then do another entangling operation. Then by just measuring the auxiliary qubit, you're not collapsing the system, and you're really able to measure, this is the picture that you see here of the atoms in one shot, the work, the quantum work that was done on the system, on the spin system. And so this is a very nice idea that Juan came to us with, and it was quite easy to show that indeed with this idea, you can make a quantum work meter. And so already with this entanglement, you can play nice tricks, but we wanted to do interferometry. So you all know about the experiment. They saw these two lines. And the question is, was it a coherent splitting? Actually, in this fest 2 years ago, there were historians also, and I asked them if Stern and Gerlach were even aware of the idea of coherence and coherent splitting. They were not sure about it, but one thing is sure. They did not prove that what they had is a coherent splitting. They could have got these two lines from their beam of silver atoms from a statistical mixture just as well. So we wanted to first prove that you could get a coherent splitting in a Stern-Gerlach apparatus. All right, so we need, the only way to prove a coherent splitting is to do some kind of interference experiment, okay? So the first thing we set out to do is an interference experiment. Now, there are many, many papers. I don't have time to review them. Actually, starting with people like Heisenberg, who used the Heisenberg uncertainty principle, but also much more recent papers that say that Stern-Gerlach splitting is impossible. Coherence in a Stern-Gerlach splitting is impossible, or very hard, at least. So, for example, this paper says that the magnets have to be cooled to cryogenic temperatures because of the noise in the classical magnets. This paper coming out of a guy who actually appeared and gave a talk in the fest in Frankfurt 2 years ago. He's coming from Los Alamos, and he says that for some reason, Einstein relativity and Schrödinger equation through a static potential forbid continuation of spin superposition through a Stern-Gerlach field. And there are more papers, these are just examples, saying that this will be very hard. And we set out to do it, to try it. By the way, there was a group in France that did for 15 years, I call them heroic beam experiments, very, very hard experiments to do. You see also that they use here many mu metal shielding, and they had partial success because these experiments were very hard to do. So what we tried to do first is to take a BC rather than a beam. So our work was much easier than what previous groups tried to do because we had a very good source of cold atoms. And now to put them in an internal superposition of spin up and spin down, and to apply a gradient. So here it's a permanent magnet, but we apply the gradient from our current carrying wires, and then a reverse gradient to stop the relative motion, and then to look if we can see, it's like a double slit experiment to see if we can see interference. So this is how the experiment looks like. And what you see here is, first of all, a pi/2 RF pulse for the internal spin superposition in the atom. Then these purple areas are just like these two areas of permanent magnets. And so these are magnetic gradients. And we apply the first one for the splitting. This is a longitudinal interferometer. So we have here one Z coordinate, and this is time. And now we mix the spins so that actually we don't have indistinguishability. We don't have distinguishability. We want to have indistinguishability. And then we have here only the two states. So with this magnet, we stop the relative motion of the two states. This is again internal spin states, but the one states, they fly away. And now we just let them expand with time of flight. They expand, they overlap, and we expect to see an interference pattern. And indeed, we could see these beautiful, very high contrast interference patterns. By the way, not only with the BEC, because there were some claims that what we see is because we actually see the coherence of the BEC. No, we also did it with a thermal cloud, and we could see also very nice interference pattern with a thermal cloud. So we started this business something like 8 years ago, as you see here, but we're still working with this kind of interferometer, which we call the half loop. Okay. Now, since people claim that by expansion, you actually increase coherence, some people even call it coherence inflation. And Ketterle has a nice paper about it, how the local coherence, when you expand a wave packet, is increasing. So some people said, well, you see it because of the increasing coherence length, because of the expansion. So we set out to do something that is harder, and that is to do a full loop. In a minute, I'll show you the full loop, where we don't have expansion at all. But before I show you the full loop, I want to show you some games that we were playing with this half loop, which are also nice. The first game we decided to play is Which Path Information. This game has been played for a long time, but we decided to give it a new twist and to see if time can serve as a which path witness. It can give us which path information. This was not originally our idea. This idea came from the Bruckner group in Vienna. We found this nice paper by their group from 2011, where they say, well, take a clock, put it in a Mach-Zehnder interferometer, and then look if you see interference. Now it's one clock, but it's in two places at the same time. And if you put it in different heights relative to Earth or relative to a mass, Einstein said in general theory of relativity that there is different proper time. If there is different proper time that each wave packet is measuring, you should see no interference if time is a measure of which path, because they will have different times. And so this is what we set out to do. And we published this in these two papers. And now we're working on an upgraded experiment, because some people have already published some loopholes, like Albert Rora published some loopholes in our experiment, and we want to now improve our experiment. So this is how the experiment looks like. We took this half loop that you saw before. Now, after we have here only the two state, we prepared a clock by a pi half pool. So these are actually the two clocks. The green clock is from this wave packet, and the red clock is from this wave packet. So these are Bloch vectors on the Bloch sphere. So to prepare a clock with the pi over 2, theta is 90 degrees. That's a good clock. And if theta is 0, it's a bad clock. So we try to put theta to bring these vectors to 90 degrees. Yeah. And then we also imitated the redshift of Earth, because the redshift is really weak. And so the difference in time between these two wave packets would be very, very small, and you need extremely good clocks. So for example, just to give you numbers, if you separate them by a meter, for a second, you get a difference of 10 to the minus 16 seconds. So it's possible to do this experiment. And I think that it will be done. And some groups around the world are trying to do it with the redshift of Earth. But this proof of principle experiment that we did 5 years ago, we did a synthetic redshift by applying here a very weak magnetic gradient. And because these clocks are magnetic sensitive, because these states are magnetic sensitive, then we were able to differentially manipulate the phi angle. The phi is the time. Phi is the time. And so we were able to do a different phi for these two with this weak synthetic redshift. And then we looked if we see interference. And so if the clocks show the same time, the two wave packets, you want to see interference. If they show a different time, you expect to see no interference. And indeed, if we look at visibility of interference here on this y-axis, and this is the redshift that we apply, which is just the length of this very weak pulse, we indeed see the theoretically expected oscillations of visibility, which prove exactly the idea put forward by the Bruckner group, as I showed you before. We even were able to think of a new complementarity rule, where, you know, the usual complementarity rule is V, which is visibility of or wave-like properties, and D is distinguishability. So instead of the usual D, we put here DGR and C, where C is a quantum property connected to theta. How good is your clock, your quantum clock is, where D comes from general relativity. How big is the time separation between the two clocks? So we actually had this distinguishability comes from two sources, from quantum and from general relativity. That was very nice. We could, of course, show it that it adheres to one, but again, not with real redshift, but with our simulated redshift. But this would be really nice if people did this with real redshift, because some people claim that we will have surprises, and maybe even this complementarity rule will be broken down when we really go into the realm of real curvature. So that would be a very nice experiment to do. But theoretically, we already saw some really interesting effects, which is that when we went into spin half, this is spin half calculation. When we went to a higher spin, we could already see that we cannot disentangle theta and phi. It's like theory is telling us that theta and phi cannot be disentangled, and maybe it's some hint about the fact that general relativity and quantum mechanics really must work together, and you cannot disentangle them. All this business is connected also to gravity-induced decoherence. This is another topic developed by the Bruckner group. And here is the postulate actually coming from that group, that in strong gravity, maybe the complementarity rule will be broken. Okay, just to flash at you, there's a big debate on which interferometers are sensitive to proper time and which not. And I'm happy to say that our interferometer is sensitive to proper time. And there were many papers some years ago about how to know if your interferometer is sensitive to proper time or not, but I will not have time to deal with it. Another very interesting spin-off of this half-loop Stern-Gerlach was this fact. Again, these are the two wave packets of the clock. So if one wave packet, we leave it here, but we now take the other wave packet here, and then we do an interference between them. We know the phase between these two wave packets. But you already know the Berry phase. The Berry phase, you have to close an area. But actually, we found out that there is another kind of phase, which is called a non-cyclic geometric phase. It's enough that you do one line, and then the geodesic closes the area for you. You don't have to complete it. This is called the non-cyclic geometric phase. So we did just the latitude, and then the geodesic closes the line. And then you have very nice connection between the regular geometric phase that everybody is connecting to this area here, and what's called the Pancharatnam phase, which is actually precedes, it's already quite old, the Pancharatnam phase, and goes back, you see here, to the 50s. And there is a connection between them, and the connection is just the dynamical phase. And you can really see it's just the different areas. I don't want to go through it, but just the different areas here on the sphere. So we took this very nice connection, and we wanted to see if that works for a half loop. And indeed, we found that in 91, somebody already made the prediction. This is our modern prediction, but it looks just like the old prediction from this paper by Bandari. And now when we look at the data, this is the Pancharatnam phase, where we see the jumps. And these jumps are every time, this thing is just theta. I told you what theta is. So we just take these and we just cross the equator with this theta. And so we just scan theta. We have these beautiful jumps, pi jumps. in the data, and you see here a pi jump actually. It's really nice to see this pi jump of the interference pattern, and the dynamic phase is very easy to see or calculate, and then you do the geometric phase and you see that it's perfect on the theory. So that was really nice to see these very sharp signals that we're now thinking maybe we can use these very sharp signals as an error signal, maybe even for gravity. So that's a nice thing that we're now thinking about how to use this as an error signal. We're also seeing other interesting effects. We just put this on the archive recently. Some freezing of the wavelength of the interference pattern, but I will not go into that. We call it periodicity jumps or rigidity, rigidity. There's some interesting effect there, but you can read about it on the archive. All right, but now I promised to you a harder Stern-Gerlach interferometer. And this is because we do not want to let the wave packet expand. We do not want this purification or this enhancement, or as people call it now, even inflation of coherence because of the expansion of the wave packet. So we want to do everything very quick. So we don't want to wait a long time for the expansion. What can we do? We do a time reversal operation. If we had here a splitting and a stopping, here we have acceleration back and stopping again. So there's a full overlap, not only in position, but also in momentum. You see now 4 areas of magnetic gradients. And this, by the way, this idea goes back more than 70 years. I think Bohm was the first one to think about it. And nobody, of course, could realize it again because there was not the technology to do it. And we decided to do it. Very different from the half loop. Here, if you don't get perfect overlap, it's called the overlap integral of momentum and position, you will see nothing. It's much harder to get here visibility or contrast. So it's an issue of actually time irreversibility. And whether or not you can really do those the second half of the interferometer, the 2 other gradients, good enough that they really undo the first 2 gradients. So this is now looking like an atom interferometer with light, which are the Kasevich-Chu, for example, which are the most common atom interferometers. And the very beautiful work done in groups like Mark Kasevich, Holger Muller, Ernst Russell, and other groups. And but they rely on the quantum accuracy of the momentum transfer, h bar k, of the photon. What is interesting is we have a classical beam splitter because it's a classical magnetic field. We do not have the quantum accuracy in momentum transfer. And it's a very interesting question whether we could reach, maybe by squeezed currents, we could reach the same accuracy in momentum transfer as these photons give these common atom interferometers. All right, so many people said this would be very, very hard. I said it started with Eisenberg, and all these very smart people actually dealt with it. In the 80s, they were, well, Bohm in the 50s said you'll need fantastic accuracy. In the 80s, Englert, Scully, and Schwinger actually published 3 papers that quantified this hard experiment. They coined it the Humpty Dumpty effect. These papers were crucial for us in order to understand what we have to do in order to get an interference pattern. And the conclusion was that it's doable, but very hard. And the contrast goes down exponentially. What do you see here? You see here the eventual, you see here the eventual imperfections and experimental imperfection in momentum relative to the initial momentum spread of the wave packet, and the eventual imprecision in position relative to the initial spread in position of the wave packet. And if your eventual imprecision, experimental imprecision, is too large, and this is micron scale, of course, this is delta Z is micron scale, it's too large, you exponentially lose your contrast. That was the outcome of this quantification that was done. And so it's hard work. And of course, people also connected to time reversal. And for example, this paper by Englert that is connecting Humpty Dumpty to time reversal. And Englert published several papers about that. Okay, so this is how the half loop looks like, which you already know. And this is the full loop. You remember that we need 4 gradients: splitting, stopping, accelerating back, and stopping in momentum and at the point of full overlap in position. And now we try to do it. And we were very happy to see that we get a very high contrast. These are now spin degrees of freedom, very high contrast in spin oscillation from this interferometer. Again, I remind you, it's a longitudinal interferometer. And now we're starting to build a transverse interferometer where both of these axes will be positioned. Yeah. And so that's an interesting interferometer, again, harder. So we'll do the full loop, but this time not in a longitudinal mode, as everybody always tried, but this time in a transverse mode. Okay, so this full loop interferometer has all kinds of interesting impacts. For example, the group of Wolfgang Schleich came to us and told us, well, there was actually a prediction from 100 years ago by Kennard, where they said that if you apply a force, and we're applying here a force all the time, yeah, if we take this TD, that's a delay time, to 0, there is a force working all the time on the particle. So what Kennard said is that if you apply force all the time, you actually get a weird T to the power of 3 phase accumulation scaling law. Whereas all the regular interferometers today, like the Ramsey-Bordet or the Mach-Zehnder, they go as T to the power of 1 or T to the power of 2. That's what people are used to. But no, Kennard said you will get T to the power of 3. And Wolfgang Schleich and his group did the theory, the modern theory for it. And indeed, they told us you will get T to the power of 3. We were very happy with this idea, and they did the theory, which I won't have time to go through. But eventually they said, if you go to TD equals 0, you see this delay time between the pulses, you only left with this T to the power of 3 terms. Yeah, this is the phase accumulation. And it could be even very large. And so we set out to do the experiment. You see the data, you see the theory from Ulm, and it sits perfectly on it, which was really, really nice to see. All right. And then papers started coming out saying that this T to the cube scaling has very fundamental features. This paper from Oxford, for example, says that it's connected to the equivalence principle, the quantum version of the equivalence principle. So again, a connection between quantum mechanics and general relativity. So we're also looking into these kinds of ideas now that people are coming up with regarding this interferometer. And now I only have a few minutes left. So I will just tell you of another harder experiment that we are dreaming of and starting to build now. So these very smart people came out 5 years ago with the following idea. If you can do a full loop Stern-Gerlach interferometer, why don't you do it on a nanodiamond with 1 spin in the middle? So it's actually an atom, just like our atom. But it has 1 spin. You can put it in a superposition of spin up and spin down. But this atom is very heavy. It weighs maybe 10 to the power of 7 or 10 to the power of 10 regular atoms. It's very heavy, yeah? But it's just a simple atom. So if we can do an internal spin superposition like we did so far, then you apply our gradients from the current carrying wires on the atom chip. You take this whole thing and put it in a superposition, spatial superposition, then you bring it back, and then you measure the spin, just like we did with the full loop Stern-Gerlach interferometer. If this could be done, then we're really in the regime of strong gravity, and then all kinds of theories could be tested on the connection between quantum mechanics and gravity, even something called self-gravity interaction, an idea that has to do with fast collapse that has to do with gravity, This is connected to ideas by Penrose. As you know, we got the Nobel last year and the Nobel Prize. And other people are also working on this idea of self-gravity interaction, or actually the idea is that these large masses would create a superposition of space-time, which is highly unstable, and create a fast collapse, much faster than we expect from regular decoherent effects. So, for example, this is a paper that recently came out on self-gravitation, but I will not have time to go into the details. People are also suggesting that we put two Stern-Gerlach full loops interferometers, one next to the other. And if they're about 100 microns, these two wave packets are about 100 microns apart, and we have 10 to the power of 9 atoms in these wave packets, then the gravitational interaction is even stronger than the spin-spin interaction. And if we manage to measure at the end, here at the end, Bell states or spin correlation, and we find that we have created entanglement, then people claim that this will be proof of the quantization of the gravitational field that went here between these two wave packets. So there are many ideas on what to do, but the experiment is very hard. And if we ever there was a feasibility study that we published recently, and you can read all about it. It's already published in Science Advances. And there's also a view of this paper in Physics World. But if we ever do manage to do this very hard experiment, it will really be because of many brilliant experimentalists and theoreticians that worked on how to do it. I just tell you what we will need. For example, Aspelmeyer and Novotny have managed to cool just this year or last year beads to the ground state, so massive object to the ground state. We will need to cool the nanodiamond to ground state, so we will use their techniques. Other people are calculating how to do rotation cooling. We'll need to do rotation cooling. Other people are thinking about or already doing experiments about nanodiamond manipulation. There was a beautiful Nature paper by Gabriele Tet on it. And so all these people, the techniques from all these people will have to use to eventually be able to do this beautiful idea of a full loop Stern-Gerlach with the nano diamond. Okay, I think I have to conclude. So the Stern-Gerlach effect, I hope I convince you, is far from completing its historical role. I again show you here the building of the original lab where 100 years ago Stern-Gerlach did their experiment. There's a lot we find all the time, and also theoreticians that come to us with ideas. We find all the time that there's a lot of undiscovered territory. We think it will also enable us to have eventually several impacts on the study of gravity, both the idea of the heavy mass with the nanodiamond, but also if we manage to do better experiments with the clocks and be sensitive to the redshift of Earth, that will also make a nice connection between gravity and quantum mechanics. And if you want to read a review about our Stern-Gerlach experiment, then thanks to Mark Kyle, we put this on the archive not long ago. And this is actually a chapter in a book that just came out in honor of Otto Stern. I think this book is actually for free, if I'm not mistaken, so you can actually download it. I think from Springer, and so all our experiments that I discussed here are in this chapter. And so these are the people that actually did the work, and this work has been going on for 8 years, and many of them are already not with us. The last one to leave us was Omer, who left for working in Garching, and in the group of Ted Hench, and before that, Yair Margalit, who did the full loop, and he went to work with Ketterle in MIT, and now all is continuing to work on these experiments. And of course, thanks to all the theoreticians that help us. And last thing I would say is that we're always searching for excellent students and postdocs, and I would be happy to hear from people if they're interested to work on this. So I thank you very much for your attention.
Well, Ron, thank you so much for this wonderful overview and sharing these exciting visions at the end. Fantastic. So towards the audience, are there questions? You might also post them into the chat or just unmute and come up with your question.
Hello, Professor Folman, thank you for a very interesting talk. So I'm actually a Berger and Blair student, and a few months ago we just published a paper in which we did a full quantum simulation of a transversal Stern-Gerlach interferometer. And basically what we did, because if you remember from this Humpty Dumpty series of papers, the crucial assumptions that factors into the result is that the magnetic field is approximate, so it does not satisfy Maxwell equations. So in our work, we actually took a full magnetic field, which does satisfy Maxwell equation, and then we just ran the simulation of the full loop transversal Stern-Gerlach interferometer. And basically what we found is that, at least for the field model that we have used, is that actually once you try to split the beams above around 30 above 30 times the width of the initial wave packet, is actually coherence gets lost, and this is purely a feature of the full magnetic field. So it's more of a remark. If you are interested in our paper, I'm happy to forward it to you.
Yes, please send it to me. Thank you very much for this wonderful comment. Please send it to me. We're really interested in any theoretical work that is being done on the Stern-Gerlach effect. And moreover, as I explained, we're now working on even harder 2D. Until now we did 1D, but we're even working on a harder 2D, where the Humpty Dumpty effect will be even harder. And so it will be really nice to compare your simulation and your calculations to our experimental results. So please send it to me and I'll be happy to be in touch.
Yeah, hi, this is Ben-Gurion. Hi, Ron.
Hi.
I sent you the link to that recent paper with Nikolai in the chat. So you can just find it there.
Thank you.
Yeah, so I just more for the audience, I'm sure Ron knows this, but there is a big difference between transverse and longitudinal Stern-Gerlach interferometer. The interferometer that was realized by the Paris group that was mentioned in the talk, there was a longitudinal interferometer, and it's easier to meet these recombination criteria in the longitudinal geometry than in the transverse geometry. It just tolerates more approximations, and also if you think about it in terms of energy conservation, you enter the inhomogeneous field and you leave the inhomogeneous field, but the kinetic energy before and after is the same. So there is no net change in the momentum, which is of course very different from the transverse geometry. So it's easier to meet the criteria for matching the wave packet. And I mean, what Nikolai mentioned is basically the observation that if you want to have an interesting interferometer, one that has enough area to do something interesting with it, you will have trouble in recovering spin coherence. And that's simply because the magnetic field is a complicated object.
Yeah. Thank you, Birch, for this comment. Yes, I agree with you that 2D is harder than 1D. That's why we did the 1D first. I have two answers. One is that the technology is improving all the time. And of course, eventually we have to adhere to Maxwell equations. But as I also mentioned before, with squeezed currents and other kinds of technology, I think that technology will surprise us eventually. but we will try. We're going to try, and so we will see. Time will tell. That's one issue. And the other issue is about the word interesting. I think that already with a 1D interferometer, you could do very interesting things. For example, all the things I showed with the nanodiamond, you could do with a 1D interferometer, or the clocks with different redshift from Earth. If we have good enough clocks, we will do it with a 1D interferometer, and you're already getting the physics that you're interested in. If it's clocks, you're getting the different height above, because you do the 1D vertically, you're getting the different height above Earth. And if it's with a nanodiamond, you're getting the self-gravity interaction because you're splitting them, even though it's 1D, you are physically splitting them. So I think that in terms of interest, even the 1D will have a lot to say and a lot to teach us. But I definitely agree that 2D is also worth pursuing just to see what are the limits that
I didn't mean to imply that the longitudinal interferometer is not interesting. Of course it is. But if you look at some of the pictures that you showed, where people want to put two transverse interferometers next to each other and have gravitational interaction in two beams that are in proximity, but not in the other beams that are far apart, there you need transverse interferometers with rather large areas. And,
yeah, so
in this geometry, it's just extremely difficult to recover spin coherence.
Yeah. So even this, what you see here, we now have a scheme to do it with 1D. Two 1D interferometers, we could do this.
Okay, that's
parallel
an improvement.
So but it's definitely a good point. But there's a lot of thinking going on about it. And I think there will still be a lot of innovation, both in technology and in terms of theoretical configurations. I think there's still a lot of stuff that we can improve.
I would like to ask a question.
Yes.
Your discussion of the sensitivity scalings with time, so linear in t square or t cubed.
T cube, yes.
So for the t and t square, let's say the atom light interferometers and those configurations that you had on your slide. So usually the time, capital T, is the time, let's say, between the pulses where you let the system evolve in order to get sensitive to a certain property that you want to measure.
Yes.
Be it magnetic fields or gravitation, yes, and etc. So now in your T3 scaling, the time between the magnetic field gradient pulses was going to 0.
No. For us, T is the pulse time, or is the interferometer time. So it's the same, because in this configuration, you can take T to also be the interferometer time, or 2T is the interferometer time. It doesn't matter, but it's interferometer time. And also for us, it's the T is the interferometer time. It's exactly the same.
But isn't that the time while you are doing something? You have the magnetic field gradients on, and then you suffer from the imperfection and the noise, and the longer that takes, the more difficult it's becoming. Whereas for the other one, nothing is happening. You can just let the system evolve, and that is not potentially harmful.
Well, first of all, even when the system evolves without anything, as all of us know, you get a lot of decoherence from the environment. It's not isolated. And if you don't apply any pulse, you get decoherence and phase noise. But you're right that this T, because it's the interferometer time, is while we do something. And it all depends, eventually our sensitivity will depend on how much noise how much noise suppression we'll be able to achieve with our. So you're completely right. And that is why I mentioned already twice, completely novel idea of going below shot noise. By the way, even most power supplies are many orders of magnitude above shot noise. But if we want to get to shot noise, and then even below shot noise, the magnetic fields are going to be more accurate than anything we have ever been able to achieve. And so I think that it could be that we'll reach a regime where this will not be the bottleneck. Yeah, and actually environmental decoherence, lack of isolation from the environment or things like that will be more harmful than actually technical noise coming on the current.
All right, thank you. Are there other questions? maybe I have another one. So your vision about the, you know, wrapping the spin into a nano diamond structure to increase the mass of that spin. Have people been thinking in that context maybe also about larger molecules that that could be cooled?
Well, of course, the state of the art in large interference pattern comes from Vienna, a group of Marcus Arndt. They already several thousand molecules of several thousand atoms. So it's beautiful. And
you're absolutely right.
What?
No, you're absolutely right. Yeah.
Yes, and so I think that is already being done, but of course, doing it in the Stern-Gerlach sense. They don't have a single spin which they manipulate, but they're doing beam experiments. And we'll see how far they manage to go with that. My feeling is that those beam experiments, which again are beautiful, beautiful experiments, will not able to reach the levels of what we will be able to reach, we and other groups that are working on it, with these nano objects. So I think the future is really in these macroscopic conditions. I think the future is really in taking nano objects and trying different methods to split them. One of the methods, Stern-Gerlach, other people would probably find other methods to split these nano objects. But they have to be cool. Of course, they have to be very cold, these nano objects, because otherwise you'll not be able to split them in a momentum difference that has to be larger than the momentum spread that you had to begin with.
The fullerenes in Marcus Arndt type of experiments, they're not cooled, right? These
no, they're very hot.
Yeah,
they're very hot.
No, I was thinking more in the direction of laser cooled molecules.
Yeah. So
and
actually, yes,
larger molecules with legions attached that you can laser cool, and then in order to cool the full molecule. That's it.
Yeah, I think it's a very interesting idea. If you can cool large molecules and have some dominant spin that you can apply a gradient onto, then that's already, that could be a wonderful Stern-Gerlach experiment with a large object. Right now, we have only succeeded to do it with a rubidium atom. It comes in with a large molecule and does it, that's already a big step forward.
All right, other questions maybe? Nothing popping up in the chat. Well, all right, then let's close the session. And thank you very much, Ron, again, for this wonderful talk and for agreeing for come here to our colloquium. All the best. Yes, all the best with the experiments for the future. Thank you very much.
And I hope to come. I hope to come to visit Singapore. I was never in Singapore, so I hope to soon come and visit.
All right. Yes. Well, it looks like it will be possible soon. Thank you.
Good. You will. Bye.